about detecting dead spruce in Norway with Sentinel-2, and we are a group of colleagues from NIBIO, and we also have one. We are very happy to have one colleague from Hungary joining our team, Tamás Molnár. He has been with us 3 times, visiting us, so we cooperate on this. But before I go into the remote sensing part, I want to give you some more background information about. So it's no, page down. Okay. Okay, yeah. So, can you see this picture? This, I mean, the main interest for the dying of spruce in Norway started in the spring, in April 2019, year after the dry summer of 2018. Then we saw a number of spruce trees that suddenly changed into red-brown in April 2019, scattered around. As you can see here, I took this out the window from an airplane. And this is a good illustration from Norway, because you can, firstly, you can get the impression of the heterogeneity of our forest. And this makes it very tricky to detect dead trees, because it's a mix of different tree species together, it's topography, and so on. So it's tricky to, so we don't have large areas with only Norway spruce. So this makes it more tricky to find them with remote sensing data. But there is also another interesting thing, and these dead spruce trees, they apparently died in the autumn of 2018 after the dry summer, probably because of polygraphus attack from August, and then they are killing the trees during the autumn, or maybe second generation of Ips typographus. So the trees actually were killed in the autumn of 2018, but they remained green during the winter. And as soon as the temperatures started to increase in April, they changed into red-brown. So there is also a delay, let's say, in the response between the drought in 2018 and the dying of the tree. Yeah, should I push the page down? Oops, I'm sorry. Oh, that then, yeah. Okay. Okay, but I have to adjust it a little bit. Like, yeah. In some cases, entire stands were killed, like this. This is unusual, but in some cases we had some high site index Norway spruce stands, very vigorous trees that suddenly died, the entire stand, in 2019. Just give you some pictures now to give an impression of the damage. I have to adjust this. And this, yeah, just also to introduce you to there's mainly 3 species of bark beetles that are killing Norway spruce in Norway. It is, of course, Ips typographus, but we have also quite some effect of Pityogenius alpographus, the small one, and also polygraphus. And in particular, the small bark beetle has been important because it sometimes has been paving the way for the spruce bark beetle, because we had quite a lot of snow damage also in 2018 and other winters, 2016 also, which means that locally the population of the small bark beetle was high. They were attacking the trees in the upper canopy, weakening the trees, and then paving the way for Ips typographus. So it's a bit complex with different tree species. And in some cases, we had dead trees with no bark beetles at all, which means that we say in this project that we are mapping dead spruce trees. We are not mapping Ips typographus killed or bark beetle killed trees, but just dead spruce trees. So the causes are sometimes complex and a bit difficult. No. And similar to what we have heard from other countries today, Finland, I think, maybe others, we have in the last 5 to 10 years had a number of different damage agents on, in particular on spruce, but also on pine. We had a big storm damage in November 2021. The picture down to the right is pine trees actually. Everything is blown over by a particular type of storm, which we call a mountain wave, very strange type of storm. Then we had severe snow damage in 2016, 2018, 2021. We had a drought in 2018, and then the bark beetle attacks. And on the map of Norway, the red area I have outlined there is the area affected by this storm in November 2021. And now today, we have problems after effects of that storm, because in the upper valleys, in the mountain areas, in the inner part of this region of Norway, it has been so difficult to take out the wind-thrown trees from the storm. So there, locally, we have high population of bark beetles, Ips typographus. More in the little bit higher elevation mountain valleys, we have locally high population and quite some severe Ips typographus damage this year, 2024. It's a kind of a long-term effect of the storm damage. While in the lowlands, it was more easy to take away the wind-thrown trees, and there the bark beetle population is low, and we have not so much damage down there. Yeah. Okay, so that was a little bit of background. I heard some of you also had some more information like that. But then we got then a project paid by the Norwegian Space Agency together with NIBIO to try to develop a monitoring service for dead spruce trees. In particular because the foresters were very interested in this. They wanted to find all new attacks, go out, remove the trees, and try to keep the population down. Because we had a severe epidemic in the 1970s in Norway, maybe some of you know that. From 1976 to 1981, we had a severe bark beetle epidemic in southeastern Norway. So the foresters still remember this damage, and they want to contribute to keep the population down. So the foresters in general were very interested in this. Can it help us to identify attack trees at an early stage so we can go out and remove them? Yeah, let's see. I have to adjust. Just we have in this project mainly used only two. This is Norwegian. Two orbits, orbit number 51 and orbit number 8, and it is mainly the violet area that we have focused on, but we have extended that a little bit during the years because that is an area with a lot of spruce, and we also had this severe epidemic in the 1970s. So based on these two orbits alone, we get new data every 2 or 3 days. So I mean, it's 50% overlap between the orbits. What we have achieved is that we have what we call the clockwork. So we have a fully automatic procedure that predict dead spruce over the area of interest and publish this on an internet service that we have at NIBIO, which is called the Kilden. So every time a new Sentinel-2 dataset is coming in, it is automatically processed, and this is then updated. So we call this clockwork, and we consider this as an achievement, even though the quality of the predictions are not really good. I have to admit, I will come back to that, but still, the system is rigged for coming up with better algorithms. We have it's not so clear here, but we have we have 3 layers. One is the probability of having dead spruce in a given pixel. The second one is a classification into 3 classes: healthy, dead, and clear cuts. And then the third layer is an aggregation into 1 by 1 kilometer pixels and the number of decars with dead spruce in that large. So that maybe you can have the impression from the lower right image that it's the 1 by 1 kilometer grid to give a kind of an overview. Yeah. So this is only published as a kind of a demonstration to some selected users that are really interested, but the quality of the predictions is not good enough to publish it normally. So we have to improve the classification considerably before we publish this as an open source. But yeah, so in this area you can see both the 1 by 1 kilometer grid, but also the scattered pixels that are predicted to be dead spruce. I think I can just drop that. It's just a legend. But then we have a very good ground truth data set. This comes from one of the biggest private forest estates in Norway called Fritzø Forest. And in 2020, they had a new forest management plan based on single tree inventory. So they had Foran Remote Sensing, a company here in Sweden, to make a single tree data set all over the 50,000 hectare land. And for every single tree, of course, it was height and so on, but also then 4 classes. It was spruce, pine, broadleaf, and dead trees. So we have then single tree information about all the dead trees, both the position, crown size, and the height of the dead trees. So this image here shows all the red circles represent the crown size of a dead tree, for example. So we have then processed these single tree data set into the 10 by 10 meter grid of Sentinel-2 as a ground truth data set. But of course, as you can get an impression here, we have very few pure pixels that are completely dead or completely healthy, or we have many completely healthy, but few pixels that are completely dead. There are almost always some mix of dead and live trees, dead and broadleaf, dead and pine trees, and so on. So that is part of the difficulty. But still, I think we consider this as quite a unique and good ground truth data set. We have then splitted this data set into one for training and one for testing. And yeah, by the way, the yellow you see here are also clear cuts. So we have clear cut as a separate category. We have just added new clear cuts into this together with the single tree data. But we haven't split the training and testing randomly because we wanted to have some blocks of data, because some of the algorithms we use, they are considering larger areas. So we have then defined some quadratic blocks for training and some quadratic blocks for testing. Yeah. Yeah. Here are the spectral signatures of the 3 classes. There is an arrow down on the legend there, but yellow means clear cut, green is a healthy tree, of course, and red is dead trees. We have updated these spectral signatures from time to time, but so I don't go in detail, but the main things to see here is that, of course, clear cuts are very easy to distinguish, in particular if you use the sphere band. band number 11 and 12, much brighter there. When it comes to the separation between healthy and dead spruce, you can see in the near infrared, it's a big difference, but also in the red, for the red band. But altogether, they are not too easy to separate. Quite some overlaps. Yeah. Right now, we have 3 algorithms, and we have some kind of internal competition between different algorithms when we compare them with some performance criteria. And right now, these are the 3 algorithms we use. I should just hit a little bit. So the first one is a convolutional neural network. It's a deep learning method with developed using RESDiNET, as we just call it CNN. It's based on save files from Sentinel-2 that we have downloaded to DBio. The code is written in Python on a Linux platform, and it's basically a time series analysis. It takes 1 year or 1.5 years and try to classify pixel based on that time series. But in addition, also has the 3x3 neighborhood spatial scale. So for every single pixel, it considers the 9 pixels around that center pixel. And that is right now, let's say, the winner of the competition. So we are using that one now for this operational clockwork service. The second one is a visual transformer, so which is developed by one of the colleagues in the project. It's also based on the same save files using Linux, written in R. And there is no temporal scale, but this is considering larger patches of pixels and trying to find groups of them. Yeah. And then the third one is more straightforward. Gradient boost is just classifying single pixels at every point in time. And the point with that one is that it uses the Google Earth engine. We just wanted to have that as an alternative to just compare the downloading of Sentinel-2 data with just processing on Google Earth engine and using then the Java program on that platform. Yeah. So let's say the first one based on time series, the second one based on the more spatial dimension of groups of pixels, and the third one just pixel by pixel classification. Yeah, maybe not expert in these algorithms myself, so maybe I shouldn't go too far into explaining this, but maybe some of you are familiar with Google Earth engine. So there are then some tools and resources here, like Sentinel-2 collection. And he has then done a spatial filtering here with a forest masking first, and then a temporal filtering, selecting the vegetation season. Then the cloud and cloud shadow masking, and then using the training data set, the gradient boost classification, and yeah, exporting the classified maps so we can analyze it more in detail. Yeah, maybe this is enough. And then for the CNN processing, the time series, I don't have much details, but I can just say that the time series contains 16 Sentinel-2 datasets starting from May in the year before and up to a given date in a given summer. So it's between, as I said, 1 year and 1.5 years. It uses all the 13 Sentinel-2 bands. It also uses the elevation, but that is probably less important. It is a little bit difficult to understand how these deep learning methods work. So he's just pouring in all the 13 bands and elevation, but we really don't know exactly how much elevation means. Yeah, and there is a simple convolution with a 3x3 neighboring pixels, and then the RESDiNET convolution across time series. This is a bit technical. I'm not expert in this, but maybe some of you understand some of it. The visual, the third method, I don't have any explanation for. I'm sorry. Then let me just give one example. This is just northeast of Oslo, where we have a hill with quite some scattered dead spruce trees. That you can see in an orthophoto. I don't know if you can see it on the screen, but if you here you can clearly see that there are groups, quite many groups of dead spruce trees in this area. And here are then the results of these three classifiers. And as you can see, they don't agree very much, I have to admit. So this illustrates the difficulty. The CNN, the time series approach, and the gradient boost, both of them have scattered pixels of dead trees, but there are quite some differences between them. And the visual transformer in the middle, it tries to find clusters of dead spruce trees, and you see these big red patches, which are not correct at all. So I just have to be honest, it's tricky, and we have quite a lot of errors in these classifications. But here is an interesting, this is one example from up in the mountains in Norway, in a place called Rødberg, where we now have a big hillside with a lot of dead spruce trees, which is quite exceptional for us. Maybe, I don't know if you can see it on the photograph, but it's quite a large area of dead spruce. And in this case, the gradient boost algorithm has really identified that you can see all the red pixels to the right here. So here, the gradient boost algorithm has really found a big patch of dead spruce trees. So right now we are collecting some large areas of dead spruce like this around Norway as a kind of an extra validation data set for 2024. Yeah. So more details about the performance for these classifications. Misdetection rate, false alarm rate, and the F1 score. I can just say that the user group of foresters that we talked to, they have told us that they want to check every single prediction that we come up with. So please minimize the number of false alarms, they told us. So because of that, we have, for the optical class 2 dead spruce, we have focused on the F1 score, but also the false alarm rate, and trying to minimize that. That has been our main performance indicator. Yeah, so if you see here, but if you start with the misdetection rate, you can see that we have quite high scores here, 63% for CNN, which is the best, 97% for the visual transformer, which means that almost all the real cases were lost, 97%. And with the gradient boost, 74%. So altogether, very many misdetections, but that is partly because we have targeted to minimize the false alarm rate, which is then, yeah, better. And here, yeah, you can see the numbers. This is for June 2020. And another example is from August 2020. It's more or less the same numbers. A little bit better for CNN now for the misdetection rates. But yeah, the false alarm rate is around 1%. It's quite low. Just adding very quickly that, I mean, detecting the clear cuts is very easy. So I don't have any performance criteria, but that is, if you just compare, this is 2018, this is 2019, we can clearly see the new clear cuts, particularly down to the right there. So finding the new clear cuts is very, very easy, and but that is not the main objective of this, of course. Okay, we have also had 2 other methods in the project. Right now, they are not part of the competition between the methods. One is extreme gradient boosting, which one of my colleagues is very keen on that method. And we used to use that algorithm for this clockwork or this routine prediction on the internet. But right now, this hasn't been updated with the last version of the ground truth, so it's not part of it, but we will compare it with the other approaches later in the autumn. Yeah, so we have gradient boosting, but not extreme gradient boosting right now. What I can just say is that maybe it's interesting for you, Langning, that the by far most important variable for the extreme gradient boosting was the DRS, which is the uppermost. So this is a variable importance plot. You see the uppermost variable is the DRS. It was very important. But as I told you in the break, we had also some problems with normalizing DRS, in particular when we have several tiles of Sentinel-2, sometimes we don't get seamless overlap between the tiles. And also if we have a lot of clouds, finding the minimum value of DRS for normalizing has been difficult. So we have struggled also a little bit with DRS and NDRS, even though it has been a very strong predictor. And yeah, just to show, this is another approach that I was working heavily on myself in 2019 when the project started. But we have put this aside now, but that was, the idea here was to make, have 2 classification algorithms, one to classify the state for every individual point in time, and one predicting the change since the previous image, and then combine the state and change and say that we only accept the change, for example, from healthy to dead, when the state classifier and the change classifier agree on that. So this is an algorithm that is currently not used in the project, but we will try to dig it up now before we end the project. So maybe we can end up with 5 different algorithms and find the best one. Okay, we have some refinement steps that we have been trying, partly with some success. One is to use the sieving to get rid of single isolated pixels here and there, which is very important, of course, for clear-cut detection, but also sometimes we can use it for dead spruce. I mean, require that at least 2 pixels together or at least 3 pixels together are classified as dead before we accept it. And the second one that we have used also earlier is that we combine a sequence of classification. So for example, if we should change a pixel from green to dead, from healthy to dead, it should be at least 2 out of the 3 last points in time that agree that the pixel is dead, because we have seen quite some variation from time to time. Two problems that we have identified is that we have sometimes errors in the geolocation of Sentinel-2, which is then due to poor topographic models for georeferencing the images. We don't have control on that, but now all the Sentinel-2 data in Norway are reprocessed with a new and better terrain model or surface model based on TandemX. So probably this problem with imprecise geolocation will be smaller. We have just tried to illustrate it here with the green line is a forest road, and maybe you can see that between these two it's slightly shifted. 1 or 2 pixels shifted between those two images. And of course, if we try to find single pixels with dead spruce trees, and there is a shift of 1 or even 2 pixels from time to time, it makes this difficult to identify this. The second problem is that we have big variations from time to time. This is just to the left is a prediction for a small area, 17th of May 2022, and to the right is the 4th of June 2022. And you can see the huge difference in predictions between these two dates. It's not so sharp here, but you can see the differences in color, which we believe is due to atmospheric effects and errors in the processing of the data to bottom of atmosphere reflectance values. So this also led us to the idea of combining sequences or predictions before we accept a change from one class to another. All right, so in conclusion, we have, I think we can call it an excellent ground truth based on the single tree data. We have this clockwork running with automatic processing and publishing the results. However, the most important thing is that we have too many classification errors. So, yeah, this was my last slide. Yeah.